In this module, we are going to take a deeper look at one specific problem, which is the mechanism design problem for selling a single indivisible object. So this is one of the simplest settings. The reason that we are going to discuss this, because even though it is the simplest setting, yet it gives certain elegant results. So let us jump into the setup. So in this setting, we have a type for player I. So which is denoted by capital Ti is the type set for player I, and an individual type will be denoted by the lowercase of Ti. Now this denotes the value of the agent. So because there is only one object, this one number represents the type completely, because if the user wins this object or gets allocated this object, then he or she gets the valuation of Ti, and if he does not get that, then his valuation is 0. Now so in this context, the allocation, let's say A is a vector of length n, which represents, now here is a slight departure, because we are now considering the probabilistic allocation of this object as well. And the ith entry represents the probability of winning the object for that player I. So you can imagine that A can be written as A1 to AN. This essentially tells you the probability. AI is the probability that player I wins that object. And therefore the set of all allocation is this simplex, where you have all this, the A's are essentially picked as a vector of length n, and they all sum to 1. And here we are considering that the object is going to be allocated to someone. It is not that it can be unallocated. Now therefore the allocation rule is mapping this type space, the Cartesian product of all these capital Ti's, into one of these allocations, one of these probabilistic allocations. And the valuation, which we usually denote with Vi of A comma Ti, which is the valuation of player I when his type is Ti and the allocation is A, is simply represented by this product form. So this is the product form, which you can think of as an expected valuation. So this is the probability with which I can win that object, and if he wins that object, he gets this value of Ti. If he does not win that object, he gets 0. So that's the expected valuation. So therefore we can actually write the f of ti comma t minus I. Note that the whole f of t, which is ti minus I, is a vector of length n. So we just look at the ith component of it, which is the probability of winning the object for agent I when the type profile is given by this ti t minus I. So this is just the notation setup. Now if you recall the victory or the second prize auction setup, there the type is actually the VI, so the valuation for player I. I mean, we are just using two different notations, TI and VI. They can be used interchangeably. They mean all the same. We are also going to define a term and a notation called T minus I, superscript 2, which is defined as follows. It is the maximum of all the valuations of all the agents except agent I. So since this is minus I, that means I is not present, and we are looking at the maximum. So in some sense you can relate this to the second highest bidder. So if I was the winner, then this would have been the second highest valuation in this population of n players. So that's the reason we write 2 on top. Now in the second prize auction, we know if agent I wins, then it must be the case the valuation of player I was larger than this t minus I of 2. So among all the other players, if you take the maximum, it is larger than that. But if it is smaller than that, then agent I does not win. And of course, the case of equality, you can have a predefined tie-breaking rule which can decide whom to give that object. Now, so this is a kind of a deterministic allocation. You give the object to the highest, the person with the highest valuation. Now we also know that the payment in that context is T minus I2. So that is the second largest bid, that is the second prize auction. If I is the winner, then he pays this much amount, T minus I2. So we can write those utilities compactly in the following way, that the utility is 0 when this Vi is less than or equal to T minus I2, and it is Vi minus T minus I2 if the valuation is larger than the second highest bid. Now what we are going to do is to draw this on a two-dimensional plane. The first figure, the figure on the left, shows the utility picture. So on the x-axis we have the valuation of player I, and on the y-axis we have the utility of player I. Now as long as this Vi is less than or equal to T minus I2, we see that the utility is going to be 0. So this has a slope of 0 in this case. And whenever it is larger than T minus I2, you can see that the utility is also increasing with the slope of 1. Right, so the second part is just drawing the figure for this expression. We know that this slope is going to be 1, and it hits the x-axis at this point T minus I2. You can also draw a corresponding allocation figure. So until T minus I2, the allocation was 0, so therefore agent I was not allocated that object, and the moment it is larger than that, it suddenly gets the full allocation. And you can actually have different allocation rules when there is a tie. Of course, we have taken one such example, but the allocation rule can be quite a large number of possibilities. So when there is a tie, you could have allocated someone else other than Vi, or it could have been a probabilistic allocation. Whatever it is, all those things are feasible allocations. Now we can make a few observations from this figure. So the first observation is that this utility is a convex function. So this is definitely a convex function, and we also see that the derivative is 0 as long as it is not winning. So the derivative of this utility is 0 as long as I is not the winner, and when it is the winner, then the derivative is 1, and it is not differentiable, we know, at that point. So the point at which this is equal to T minus I2, this convex curve is not differentiable. But the other observation is that whenever it is differentiable, it actually coincides with the allocation probability. So you look at this, we told that at the point T minus I2, the allocation could take any value, so it does not really matter. But whenever it is a winner, clear winner here or here, the derivative here is actually, so the derivative of this utility function is actually the allocation here, right? And similarly here, this is the slope that was 0, and allocation was also 0. So these are two important things that we will come back to when we actually give some results. We actually prove a very important result for single object allocation. We will actually look at characterizing the DSIC mechanisms in a slightly different way. Now, to prove that, we need certain known facts from convex analysis, and we will not try to prove all these results because they are actually quite involved. Rather, I would direct the reader to see a standard text, something like Rockefeller or Bartsekas, to have a look on this results of convex analysis. So first two facts. So convex functions have this property that they are continuous in the interior of its domain. What can happen is that the jumps can only occur at the boundaries, and the intuition is that if you have a jump at some point, then this function is clearly not convex, because you can have a chord which connects these 2 points, And the requirement of a convex function is that this chord should always lie above that curve, which cannot happen in this case. So as long as you are in the interior of the domain, the convex function is always going to be continuous. Of course, at the end, whenever, so suppose you have an end and then you have a jump here, because there is no other point beyond this domain, you can have a jump, and that will still be convex, because you cannot draw a chord which goes even beyond. But it can never be discontinuous inside the interior of this domain. The second fact of convex functions is that it is differentiable almost everywhere. So what does that mean? So it says that the points where the functions are not differentiable, this function, let's say a convex function, I collect together all the points where this function is not differentiable, they form a countable set. You can take a look at this from another standard text. So in some cases it is called the measure zero set. So the set of points where the convex function is not differentiable, they form a set of measure zero. So in the previous example, you can see that it has a non-differentiability here. There can be few other such points, but they all will be finite, or at most a countable number of sets. There cannot be an interval, for instance, where this function is not differentiable. That is not possible. Now, just to recall, I am sure that you already know it, but just for completeness, let us just formally say what a convex function is. So a convex function, a function g, which maps an interval. So in this context, we are just going to deal with intervals, real line intervals. This function maps to the real numbers, set of real numbers. It is convex if you take the convex sum. So this is the chord that we are going to talk about. So you take, so the function has 2 points, x and y. You take the values gx and gy at these 2 points, and take a convex combination of these 2 points. That line should always stay above any point that you take in between. So you look at the corresponding the convex combination of those x and y's, and try to find out what is the value of that function g at that point that will lie below this chord. So that is the notion of convex function. Now we are also going to define using this notation g prime x. If g is differentiable at this point x, which is in this I, then we will denote this derivative by g prime x. And now we are going to actually extend this definition of gradient, or the derivative. So we are going to call something called a subgradient. So we are going to say that for any x, a point x in that interval, x star is a subgradient of this function g at that point x, if the following thing happens. If you take any g of z, any other point, then it must be greater than or equal to gx plus this number, the subgradient, multiplied by z minus x, and this should hold for all z in I. So this might look a little daunting at times, but let us look at an example to understand this point of subgradient. So let us look at this point x, this green x, right? And suppose this function, the function is gx. So the x-axis is going to represent that value x, and we are focusing on one point, which is this x. We see that this is non-differentiable here. Now even though if it is not differentiable, we cannot define a gradient in the usual way, but we can define a subgradient. How? So now let us look at any arbitrary point, let's say z1 here. Now what we can find out is that this point here, if you look at this point, and suppose we have also fixed this x star, which is the slope here of this green line, green dotted line. Now this point is nothing but gx plus x star multiplied by z1 minus x. So this is the standard thing. You have this z1 minus x multiplied by the slope x star, then you get this point. Now what the subgradient is telling you is that when you look at the value of the function at z1, that should lie above this point, this combination here. Similarly, when you go the other direction, now you know that z2 is smaller than x, so therefore this term essentially is negative. So you have gx minus of that value multiplied by this x star. That will lead you to this point here, and also the value of g of z2 at that point is above this value. So in some sense, this line, this green dotted line, is acting as a support. The whole curve, the convex curve, should be above that line. And you can also see that this x star is not unique. You can also draw a different line, and that will also be a different a subgradient. Or you can draw a different line, and that will also be a subgradient. All these are valid subgradients at this point x. Now, so that is one observation, that you have many possibilities for x star when you are looking at this green x here. But if you look at this red x here, then you have only one x star possible. You can see that if you look at this point here, you cannot really have multiple x stars. So for instance, this will not be a subgradient, because so the curve actually goes below this point at some z's, which also belongs to I. So therefore the only possibility is the gradient. The gradient actually coincides with the subgradient when the function g is differentiable. So that is one of this lemma. This is also coming from the convex analysis text. We will not prove it. So if the function is convex and suppose x is in the interior of I, so this is a technical requirement, it has to be at the interior, not at the boundaries. And if g is differentiable at x, then this g prime x is the unique subgradient of g. So the derivative will be the unique subgradient. The other lemma is guaranteeing the existence of a subgradient. So it says that if g is a convex function, then for every point x in this interval, a subgradient must exist. And this is also quite easy to see. Whenever there is a convex function, you can always find a kind of a supporting line so that the curve always lives above. The convex curve always lives above. So that is the intuition, but it can be proved more formally. So we denote by this notation I prime, which is a subset of I, to be the set of points where g is differentiable. Note that we know that the set of points where it is not differentiable has a measure 0. Then this fact is saying that the set of subgradients at a point forms a convex set. So we saw the cases where the gradient does not exist, that is, the function is not differentiable. There can be the subgradients can be non-unique. There can be many subgradients. But if you collect together all the subgradients, they will again form a convex set. And we can also give a very nice structure of that convex set. So imagine that we are looking at the derivative. We know that at a particular point at x, the derivative does not exist. But we know that there exist, so because those points can only be kind of countable, they are of measure 0. So there is a much larger set on which it is actually differentiable. So we are actually approaching that point x. So let us go back to that example. So suppose at this point green x, the function is not differentiable, so we are actually approaching to x from the left. So actually in this case we are approaching it from the right. So z, we are looking at z, which is larger than x, and we are looking at the derivative. So we are actually approaching it from right. So you find out the derivative. So here we know that the derivative exists, and we are actually trying to get to the point to the right limit of that derivative when we approach x. Similarly, we can do the same thing and find these two different numbers, which are the limits of those derivatives when you approach x from right and when you approach x from left. And we denote those with g plus prime of x and g minus prime of x. Now the next fact is actually telling us that the set of subgradients at those x's where it is not differentiable is actually given by this interval. So we know that by the previous fact that the subgradients are forming a convex set, and this fact is actually telling you what that convex set will be. It will be another interval, and you can find the interval by finding the limits of the corresponding derivatives. Just for a shorthand, we will use this notation del of g of x to denote the set of subgradients of g at a point x. And note that that if you are in the set where you the function is differentiable, therefore then this set will be a singleton. Otherwise it will be an interval, but all that we know from lemma 2 is that this will always be non-empty for any x. So the subgradient will always exist at every point in the domain of that function g. There are two more crucial lemmas which will be quite useful when we go to the next part to discuss more about the single object allocation problem. So if we have a function g, so let's say that is a convex function, and we are going to define a function called a subgradient function, which also maps this i's to r's. Now the property that it has is that at the points where the function is not differentiable, you can have multiple subgradients. Now this function phi is picking one of those subgradients for each of those points where it is not differentiable, and that function is going to give me one specific subgradient function. There can be many subgradient functions. Actually there'll be uncountably many if we have one or more points which are non-differentiable for this function g. Now if you fix that function phi, then what we can say is that for all x and y, this subgradient function will be non-decreasing. So a very simple way to look at it is that when you have a function which does not have any, the convex function that we are dealing with is differentiable at all points, then the derivative of that convex function should be non-decreasing. That is one of the requirements of a convex function. So it is actually generalizing that. It is saying that if you have a subgradient function, that will also be non-decreasing. And now we are going to discuss about the last result in this short module of convex analysis. So this actually gives you an integral formula. Whenever you are trying to find a value of the function at a certain point, then this integral formula will be very useful. So what it is saying, if you are trying to find the value of g of x, then you can start at y and take the integral of that subgradient function starting from y to x, integrate that, and that will be equal to the value of the g of x. So where we know that this function phi is essentially a subgradient function. So this essentially gives a kind of a very high level idea about few results in convex analysis. We are going to use some of these results in the following modules.